So let us start with computer networking. You will learn to describe what is a network. Then we will see different types of examples of network in our day-to-day life. Then we will describe the standard definition of computer network, and finally we will conclude our next lecture with characteristics of networking. So, what is a network? A network is nothing more than two or more computers connected to each other so that they can exchange information such as emails, messages, or documents, or they can share resources such as disk storage or printers. In most cases, this connection is made via electrical cables that carry the information in the form of electrical signals. But in some cases, the type of connections are used. For example, fiber optic cables let computers communicate at extremely high speeds by using impulses of light. So, standard definition of computer network goes as follows. To be specific with computer technology, a network is a connection of two or more computers that are linked to each other in order to carry out tasks such as printing, sharing data, exchange of electronic media, etc. So, what are the characteristics of a computer network? Well, the major advantage of a computer network is sharing of resources from one device to another device. Then, we can also create and store files onto different PCs located in the network. We can access files from different computers. We can connect input-output devices to a computer. It allows us to share databases on different servers, and it also minimizes cost consumption. There are many types of networks such as local area network, wide area network, metropolitan area network, and many more. So, let us have a quick recap. We discussed what is a network, we discussed the definition of a computer network, we saw real life examples of computer network like a group of friends, and finally characteristics of computer networks. What's next? Once we know the definition of computer network, we move on to the topologies in computer networks. Let us start with network topologies. In this lecture, we will define a network topology and we will also see different types of network topologies. The term network topology refers to the shape of how the computers and other network components are connected to each other. There are several different types of network topologies, each with advantages and disadvantages. Talking in technical terms, a network topology is an interconnection of various computers in a specific way, which includes a connection between two computers using cables. Also, the arrangement of a network which comprises of nodes and connecting lines via sender and receiver is referred to as network topology. So, let us start exploring different types of topologies. The first one is the mesh topology. In mesh topology, every device is connected to another device via a particular channel. If suppose there are n number of devices connected with each other in a mesh topology, the total number of dedicated links required to connect each other is n into bracket n minus 1 upon 2. So, in the above diagram which is in front of you, we can see that there are 5 PCs. So, total number of links required to connect each PC with one another is 5 into bracket 5 minus 1 upon 2, which equals to 10. Now, what are advantages of using this topology? Firstly, mesh topology is a robust topology. If a fault is diagnosed, it can be detected very easily. Data is reliable because data is transferred among the devices through dedicated channels or links and provides security and privacy. What are the problems with this topology? Installation and configuration is very difficult. Cost of cables are also high as bulk wiring is required, hence suitable for less number of devices. Moving on to our next topology, that is star topology. In star topology, all the devices are connected to a single hub through a cable. This hub is the central node and all other nodes are connected to the central node. The hub can be passive in nature or intelligent hub, that is an active hub. So, what are the advantages of star topology? If n devices are connected to each other in star topology, then the number of cables required to connect them is n. In the figure, you can see that there are 4 PCs. Therefore, we need 4 cables to connect those PCs to the central hub. What are the problems with this topology? If the hub fails, what will happen? The entire topology fails, right? Also, the cost of installation is high. And the major point is performance of this topology is entirely dependent upon the hub. Moving on to the next topology, that is ring topology. In this topology, it forms a ring connecting devices with its exactly 2 neighboring devices. The following operations take place in the ring topology. Please listen clearly. One station is known as a monitor station, which takes place all the responsibility to perform the operations. To transmit the data, the station has to hold a token. After the transmission is done, the token is to be released for other stations to use. When no station is transmitting the data, then the token will be circulated in the ring. Now, there are 2 types of token release techniques, early token and delay token. Right now, we do not need to go into the details of these technologies. The next one is the bus topology. Bus topology is a network type in which every computer and network device is connected to a single cable. It transmits data from one end to another end in a single direction. No bidirectional feature is available in bus topology. So, if n devices are connected to each other in a bus topology, then the number of cables required to connect them is 1, which is known as the backbone cable. So, you can see in the image that bold blue line is the backbone cable and the red lines are the drop lines. What is the problem with this technology? Suppose if the common cable fails, then the whole system will crash down, right? And if the network traffic is heavy, it increases the collisions in the network. And here comes the last topology, that is the hybrid topology. This topology is a collection of 2 or more topologies which are described above. This is a scalable topology which can be expanded easily. It is a reliable one, but at the same time it is a costly topology. So let us have a quick recap. We saw the definition of topology, then we saw different types of topology. So now you must be able to identify which topology is used in your campus. And what's next? Since we have discussed about the topologies and definition of computer networks, it's time to see when computer networks was invented. So in the next lecture, we will talk about history and applications of networking. Let us start the history of computer networking. In today's hypertech world, almost any new device is born smart enough to connect easily with the global network. This is possible because at the core of this worldwide infrastructure lies what we call the Internet, which is a set of shared communication standards, procedures and formats called protocols. The foundation was laid by the ARPANET. It was established by the United States Department of Defense. ARPANET, which is Advanced Research Projects Agency Network, was an experimental computer network that was the forerunner of the Internet. Its initial purpose was to link computers at research institutions over telephone lines. It was the first wide area packet switching network with distributed control and the first network to implement the TCP/IP protocol suite, which we will be learning in the further lectures. The first network was led between University of California at Los Angeles and the Stanford Research Institute, and then it expanded from Illinois up to New York and Washington, thereby covering the entire United States. Wow, Internet. You might have heard of this term. This term was coined by Winton Cerf, Eugen Dalal, and Carl Sunshine of Stanford University to describe this network of networks. ARPANET was expanded to connect DoD with those universities of the US that were carrying out defense-related research. The concept of networking got a boost when University College of London and Royal Radar Network, Norway, connected to the ARPANET and a network of networks was formed, which is Internet. Telnet. Telnet is a network protocol used to virtually access a computer and to provide a two-way collaborative communication channel between two machines. It follows a user transmission control protocol, that is TCP/IP protocol. Through Telnet, users can log on as a regular user with the privileges they are guaranteed on the specific applications and data on the computer. Here the concept of Internet Service Provider, that is ISP, was introduced, which is the main backbone of networking in today's world. So, can you recognize what is this? Yes, it's the WWW, that is World Wide Web. You might have heard of WWW right from your childhood. The general definition for a layman can be the three W's seen in any URL. In 1980, the Tim Berners-Lee, based in Switzerland, invented the World Wide Web. WWW is a global information medium which users can access via computers connected to the internet. But this term is often mistakenly used as a synonym for the internet itself and often called as internet. Like if you ask a random person what is www, they can easily say it's internet. But the web is a service that operates over the internet, just as email. www is a complex web of websites and web pages connected to the internet. So, as you can see, in 1957, ARPANET was formed by the United States. In 1967, ARPANET became functional. In 1970, ARPANET connected to the BBNs. Now what is a BBN? BBN stands for Broadband Networking Services. In 1972, email was developed and symbol @ came into use. In 1974, the term Internet was coined and also Telnet was approved. In 1982, TCP/IP was introduced as a standard protocol. In 1983, the DNS was born. In 1986, NSFNET program enhances connectivity. It enhanced the connections across the world. In 1990, the first web browser, Nexus, was developed by HTML. In 2002 to 2004, Web 2.0 was born. And till date, you can see the world is full of networks. So, in order to protect everything around the globe, we need cybersecurity. And this is where networking is very important while you learn cybersecurity. So, what are the applications of networking? Well, web, emails, then downloading and uploading files, cloud computing, groupware, that is video calls and chatting, right? You have a video call with your friends, well, that is an application of networking, and also some standalone applications. Let us have a quick recap. We saw how the internet was born, we saw what is ARPANET, we saw how the first message was exchanged between two different places, and then we discussed about applications of network. In the next lecture, we will see what are protocols and why protocols are important, and why do protocols make really important a connection in a computer network. So, let us begin with the protocols and standards. In this lecture, we will define Two widely used terms, protocols and standards. First, we define protocol, which is synonymous with the rule. Then we discuss standards, which are agreed upon rules. So, what is a protocol? In computer networks, communication occurs between entities in different systems. An entity is anything capable of sending or receiving information. However, two entities cannot simply send bits of streams to each other and expect to be understood. For communication to occur, the entities must agree on a protocol. A protocol is a set of rules that govern data communications. Protocol defines what is communicated, how it is communicated, and when it is communicated. For example, when you talk to your friend, if your friend start talking randomly, you will understand it's gibberish, right? You won't understand what he or she is saying. And therefore, there are grammatical rules which are protocols for English language. The three key elements of a protocol are syntax, semantics, and its timing. Let's explore these three terms in detail. So, what is syntax? The term syntax refers to the structure or format of the data, meaning the order in which they are presented. For example, a simple protocol might expect the first 8 bits of data to be the address of the sender and the second 8 bits data to be the address of the receiver and the rest of the stream to be the message itself. Semantics. The word semantics refers to the meaning of each section of bits. How is a particular pattern to be interpreted and what action is to be taken based on that interpretation. For example, does an address identify the route to be taken or the final destination of the message? And the last one is timing. The term timing refers to two characteristics: when data should be sent and how fast they can be sent. For example, if your internet service provider produces data at 100 Mbps but your mobile device can only receive or process data at 1 Mbps, the transmission will overload and some data will be lost. Now, here is an example of some protocols: ARP, that is Address Resolution Protocol, HTTPS, FTP, that is File Transfer Protocol. Don't worry, we are going to explore all these protocols in the next lectures. And here come the standards, which are agreed upon rules. Standards are essential in creating and maintaining an open and competitive market for equipment manufacturers and in guaranteeing national and international interoperability. Right? Internet standard. What is an internet standard? An internet standard is a thoroughly tested specification that is useful to and adhered by to those who work with the internet. It is a formalized regulation that must be followed. There is a strict procedure by which a specification attains internet standard status. A specification begins as an internet draft. So, these are some standards for transport layer. For example, TCP, SPX. For network layer, it is IP and IPX. For data link layer, it is Ethernet, IEEE 802.3, X25 and frame relay. Let us have a quick recap on what we have learned. So we saw what are protocols, we discussed the key elements of protocols and also discussed the importance of those protocols. Then we discussed about standards and saw some examples of standards.
Let's start with the OSI model. In this video, you will learn to describe the OSI model. The Open System Interconnection Model is a 7-layer model used to visualize computer networks. The OSI model is often viewed as a complicated and many fear having to learn the model. However, the OSI model is an extremely useful tool for development and problem solving. Each of these 7 layers goes up in increments of 1 as it gets closer to the human user. The application layer is closest to the person, while the physical layer is where the network receives and transmits raw data. In plain English, the OSI provides a standard for different computer systems to be able to communicate with each other. The OSI model consists of 7 layers. The first is the physical layer, then data link layer, network layer, transport layer, session layer, presentation layer, and the application layer. The prime difference between the TCP/IP model and the OSI model is that the TCP/IP model does not have 2 layers, that is the presentation layer and the session layer. So, have you ever imagined how does your WhatsApp message gets delivered to your friend? Well, this is how it looks. First, to communicate with your friend you need a physical connection, that is cables and the coaxial cables which reside on the physical layer. Even though you are connected physically, you need to address yourself, that is the MAC address which resides on the data link layer. So have you ever wondered what is a MAC address? MAC is a physical address for your device through which devices in a network identify your device. Now you have a MAC and a physical connection. All you need is a logical address, that is an IP address which resides on the network layer. Now you have a good setup of network with physical links and addresses, but how do you communicate? All you need is a protocol which transfers data from yourself to your friend, that is TCP and UDP, which resides on the transport layer. There should be an intermediate node which manages the setting up and taking down of the association between two communicating endpoints, that is called as a connection. This is done by the session layer. The data flows in a network will be in the form of ones and zeros. So there should be a node which translates those ones and zeros to plain text, that is the human readable format, and if necessary, compression and decompression. This is done by the presentation layer. Finally, what you see on your monitor is the final application and the result of combination of all these protocols. This can be done by some specific protocols like HTTP and HTTPS which reside on the application layer. So, let us have a quick recap over what we learned in this lecture. The OSI model helps to divide a network in 7 layers. These layers are easy to understand for any network communication. The first 3 layers are the responsibility of the network and the next 4 layers are the responsibility of the host. Each layer have their own roles and responsibilities. Similarly, network devices work on specific OSI layer. So in the next lecture, we will see the 7 layers of the OSI model.
In this video, I am going to cover the OSI model. The Open System Interconnection Model, OSI, is a 7-layer model used to visualize computer networks. The OSI model is often viewed as complicated and many fear having to learn the model. However, the OSI model is an extremely useful tool for development and problem solving. Each of these 7 layers goes up in increments of 1 as it gets closer to the human user. The application layer is closest to the person, while the physical layer is where the network receives and transmits raw data. In plain English, the OSI provides a standard for different computer systems to be able to communicate with each other. The 7 layers of OSI model are the physical layer, data link layer, network layer, transport layer, session layer, presentation layer, and the application layer. The 2 layers, session layer and the presentation layer, are extra in the OSI model as with respect to the TCP/IP model. This is how you send a message to a friend. I would like to demonstrate with an example. Firstly, you want to communicate with your neighbor system, you need a physical connection. It is cables, coax, the physical layer. Even though you are connected physically, you need to address yourself, that is MAC, the data link layer. MAC is a physical address for your device. Basically Ethernet, Wi-Fi, etc. Now, you have a MAC and a physical connection. All you need is a logical address, that is IP, the network layer. Now, you have a good setup of network with physical links and addresses. But how do you communicate? All you need is a protocol which transfers data from your system to another, that is the TCP or UDP, the transport layer. There should be an intermediate node which manages the setting up and taking down of the association between two communicating endpoints, that is called connection. that is done by the session layer. The data flows in a network will be in the form of ones and zeros. So there should be a node which translates the ones and zeros to plain text, that is the human readable format, and if necessary, compression and decompression. This is done by the presentation layer. Finally, what you see in your monitor or mobile is the final application and the result of the combination of all these protocols. This can be done by the application layer, the HTTP and the HTTPS. The first three layers are responsibility of the network, and the next four layers are the responsibility of the host. The layers of the OSI model. First comes the physical layer. The physical layer is literally the physical hardware that makes up the network. This layer has several major functions: defining physical specifications, defining protocols, defining transmission mode, that is half duplex and full duplex, defining the network's topology. Hardware such as the physical components of the Ethernet cables and the Bluetooth are just some examples of the physical layer. This is also the layer where the data gets converted into a bit stream, which is a string of ones and zeros. Generally in computer system, 1 stands for true and 0 stands for false. The next comes the data link layer. The data link layer is very similar to the network layer, except the data link layer facilitates data transfer between two devices on the same network. Data link layer is where switches operate and provides a reliable link between two directly connected nodes. Data link layer is also responsible for detecting and possibly fixing any packet errors that may form on a physical layer. Next comes the network layer. The network layer is responsible for facilitating data transfer between two different networks. If the two devices communicating are on the same network, the network layer is unnecessary. The network layer also finds the best physical path for the data to reach its destination. This is known as routing. This is where your IP address comes from. The router is responsible for sending packets of information out into the internet and then receiving them. These packets' origin and destination is determined by the IP address of your router. The next is the transport layer. The transport layer is responsible for end-to-end communication between two devices. As I've shown the truck between the two devices. The transport layer is responsible for the logistics of the session. The transport layer would be responsible for determining what and how much information is transferred between the operating system and the web server. Next is the session layer. This is the layer responsible for opening and closing communication between the two devices. The session layer is responsible for creating and maintaining sessions between the operating system on the presentation layer and the other third-party machines. For example, when a user is browsing the internet, they are interacting with the application layer. The application layer is interacting with the presentation layer, and the session layer allows the operating system to interact with the web server. Yeah, this is a bit complex thing. The session layer ensures that the session stays open long enough to transfer all the data being exchanged and then promptly closes the session in order to avoid wasting of resources. The sixth layer is the presentation layer. This layer is primarily responsible for preparing data so that it can be used by the application layer. The presentation layer is also responsible for translation, encryption, and compression of data. The presentation layer is where the operating system lies. This operating system could be Windows, OS, or any Unix-based operating system, or one of the many applicable. When the human user interacts with the application layer described above, the application layer interacts with the presentation layer. If the devices are communicating over an encrypted connection, presentation layer is responsible for adding the encryption on the sender's end as well as decoding the encryption on the receiver's end so that it can present the application layer with unencrypted and readable data. This is the most important point of the presentation layer. The application layer. The application layer is where the user inputs data and data is output to the user. Software applications like web browsers and email clients rely on the application layer to initiate communications. But it should be made clear that the client software applications are not the part of the application layer. Rather, the application layer is responsible for the protocols and data manipulation that the software relies on to present meaningful data to the user. Client software is a specific application that's installed on your computer that can be used to communicate to some other piece of the software over a network, such as Internet's World Wide Web. Microsoft Outlook on your desktop is a software client, and indeed web browser are software clients. An example of the application layer is an internet browser, an FTP client, or even Microsoft Word. The advantages of OSI model. OSI model breaks down complex world of networking into a single model. OSI model is basically a generic model, and that is including a whole group of things. OSI model is a well distinguished model, that is all the layers are well distinguished and separated. Supports connection oriented and connectionless services, more secure and adaptable. The disadvantages of OSI model. Basically, it is a theoretical model which does not guarantee efficient technology. Inadequate solution for practical network implementation. When OSI appeared, the TCP/IP protocols were already implemented. This is the main disadvantages of the OSI model. The layers cannot work in parallel.
So, let us start learning the TCP/IP protocol suite. In this video, we will learn to describe what is TCP/IP model, and we will have a brief overview of TCP/IP model. So, what is TCP/IP model? The Internet Protocol is like any other communication protocol, is a set of rules which will govern every possible communication over the Internet. Since the development of the ARPANET, TCP/IP together has emerged as the controlling body. It is being used in the computers of not only in the United States but all over the world for all the types of and sizes of computers. It has become the language of the Internet. TCP/IP are two protocols, Transmission Control Protocol and Internet Protocol. These two protocols describe the movement of data between the host computers on the Internet. This new architecture is known as TCP/IP reference model due to the use of two protocols TCP and IP. So, while designing the new model, certain goals were to be achieved. I will tell a few of them. First was the design goal, which was to have an ability to connect multiple networks together in a seamless way. Another goal was that the network should be able to survive loss of subnet hardware with existing conversation not being broken. And the last one was a flexible architecture was needed to deal successfully with the divergent requirements of various applications. So, the overview of TCP/IP model is as follows. TCP/IP offers a simple naming and addressing scheme whereby different resources on the Internet can easily be located. Information on the Internet is carried in packets. The IP protocol is used to put a message into a packet. Each packet has the address of a sender and the recipient's address. These addresses are known as IP addresses, which we will be learning in upcoming lectures. ARPA originally created TCP/IP to connect military networks together, but later on, this protocol was also given to government agencies and universities free of cost. TCP/IP model is most widely used because it is robust to failures and flexible to diverse networks. TCP/IP became the standard for Unix computers, especially in the military and university environments. With the development of HTTPS protocol for sharing HTML language freely on the Internet, the World Wide Web was born, and soon TCP/IP came into much use. So let's have a look at the TCP/IP model. In the picture you can see that I have shown 5 layers, but 4 layers are also used interchangeably. The data link layer and the physical layer is together known as host to network layer. So the 5-layer model consists of the following 5 layers: application layer, transport layer, network layer, data link layer, and the physical layer. Since the 5-layer model is basically a communication model to be explained in layman's terms, hence I will understand it using a real-life communication example. Now, for the explanation purposes, I will demonstrate it in 4-layer model. Let us consider Bob and Peter are two friends who live in different cities, say city A and city B. It is Peter's birthday and Bob has decided to send his friend a Harry Potter series book as a birthday gift. So in this case, Bob is the sender, that is source, and Peter is the intended receiver, that is destination. Now there are 7 books in the Harry Potter series, say each weighing 1 kg. So Bob packs all the 7 books into an envelope weighing 7 kg in total. The envelope has Bob's address and Peter's address as well. The following is a detailed discussion on how this transfer of books takes place, so please make sure that you listen carefully. Let us see what happens at the application layer. Bob goes to the nearby post box and puts the 7 kg envelope into the post box. Here, Bob's job is finished. Bob does not have to concern about how the postman carries out his job. This part, where Bob puts the 7 kg envelope into the post box, is nothing but our application layer. Moving on to the next layer. Now, when the postman arrives into the post box, he collects the envelopes in it, along with Bob's 7 kg envelope. But the sorting office only takes in a package weighing maximum of 1 kg. Due to this, the postman does the following. He takes out all the 7 books out of Bob's envelope, puts each book into a single envelope weighing 1 kg, writes Bob's address and Peter's address on all the 7 envelopes. Finally, he deposits all the 7 envelopes to the sorting office of city A. Now, here postman's job is finished. He does not have to concern himself about how the sorting office delivers the envelopes to their discussion. That is, postman doesn't have to worry about the details of how sorting office carries out its job. So you must have now got it. This part where the postman puts each book into different envelope and writes the sender and the receiver's address on each envelope and delivers those envelopes is nothing but the transport layer. Moving on to the network layer. Now since the sorting office of city A has all of the Bob's envelopes, they have to send those envelopes to city B so that they can be delivered to Peter. But there are some rules that have to be followed by the sorting offices. Like the envelope must have a postal stamp on it, the envelope should have a proper sender and receiver's address, the destination should be inside the same country as that of the senders. Sending offices make sure that all the rules are being followed properly. Also, to send envelopes to different cities, the sorting office has to take help of a courier service. For example, the sorting office pays a carrier service to carry the envelope to different cities. So, the sorting office now hands over the envelope to carrier service. So this part where the sorting office checks all the rules and hands over the envelope to carrier service is the network layer. And finally comes the last layer, which is a combination of data link layer and the physical layer. Now our carrier service has got all the envelopes and it has to send them to city B. The carrier service can carry out its job in many ways, like they can carry the envelopes via airplanes, or they can carry the envelopes via bus or via ships. But remember that only one option is taken, either bus or airplane or ship. Suppose it decides to take the air travel option. After the package arrives at the destination of city B's airport, the carrier service delivers them to the sorting office of city B. Carrier service's job is finished here. So, this part where the carrier service takes place the envelopes from one city to another via medium is a link layer. Putting it in order, you can consider Bob as the sender, envelope of 7 kg is data, post box is the front end application, putting each box into separate envelope is nothing but network layer, each 1 kg envelope is a data packet, postman is the transport layer protocol service, sorting office as network layer protocol, carrier service as link layer protocol, and Peter as the intended recipient of data. So, by now you must have understood the complete working of TCP/IP layers and how these layers act. So, let us have a quick recap. We saw how TCP/IP layers worked and it was a big discussion. So if you haven't understood, you should go and read the again and listen to the explanation again to get a better idea of working of TCP/IP model. Make sure that you understand all these concepts very clearly because these are the fundamental concepts in networking. What's next? Now we will see the layers of TCP/IP model in technical terms, and we'll also see the comparison between OSI model and TCP/IP model. Welcome to another lecture where we'll see the difference between OSI model and TCP/IP model. But before moving ahead, I would like to first describe the layers of TCP/IP model in technical terms. As you can see, the TCP/IP model consists of 5 layers, or the physical layer and data link layer together is known as host to network layer, thus making it a 4-layer model. So, the application layer. TCP/IP model does not have session or presentation layers because they are of little importance in most of the applications. The layer on top of the transport layer is called as the application layer. The protocols related to this layer are all high-level protocols such as Telnet, FTP, Simple Mail Transfer Protocol, and many more. Many other protocols have been added to these over years such as Domain Name Service, NNTP, and HTTP, etc. Then the transport layer. This is the layer above the internet layer or the network layer. Its functions are same as those of transport layer in the OSI layer. This layer allows the peer entities of the source and destination machine to converse with each other. The end-to-end protocols used here are TCP and UDP. TCP is a reliable connection-oriented protocol, whereas UDP is a connectionless protocol. It is an unreliable connectionless protocol and used for the applications which do not want the TCP's sequencing or flow control. The next comes the internet layer, also known as the network layer. This layer is called as the internet layer and it holds the whole architecture together. The task of this layer is to allow the host to insert packets into any network and then make them travel independently to the destination. The order in which the packets are received can be different from the sequence in which they were sent. Then the higher layers are supposed to arrange them in the proper order. Note that internet is being used as a generic term. The network layer is supposed to deliver IP packets to the destinations. So, now what is the difference between all these layers? In OSI there are 7 layers as you can see, but in TCP/IP it has 5 layers or 4 layers. Transport layer guarantees delivery of packets in OSI model, whereas there is no delivery of packets in TCP/IP model. OSI model follows a horizontal approach, whereas TCP/IP model follows a vertical approach. OSI model has a separate presentation layer, whereas TCP/IP model doesn't have session as well as a presentation layer. OSI model is a truly general model, whereas TCP/IP model cannot be used for any other application. OSI model has a problem of protocol fitting into a model, whereas TCP/IP model does not fit any other protocol stack. So, let us have a quick recap. In both the models, the functions of layers is approximately the same. Both the models use the concept of layered architecture. The transport layers and the layers below it provide transport independent services, and in both the models, the layers above transport layer are application oriented. So, in the next lecture, we will have an introduction to addresses in computer networking, and we will see why addressing is very important and also discuss the different types of addresses in computer networks. let us get to know the description of addresses. So, in this lecture, we will talk about Ethernet address or MAC address, also known as the physical address. Then we will see what is logical address, and after that we will see what is a port address. What is a physical address? In order to communicate or transfer the data from one computer to another computer, we need some address. In computer network, various types of addresses are introduced. Each works at a different layer. Media access control address, that is a MAC address, is a physical address which works at data link layer. In this lecture, we will discuss about addressing in DLL, which is MAC addressing. The physical address, also known as the link address, is the address of a node as defined by its LAN or WAN. It is included in the frame used by the data link layer. It is the lowest level address. The physical address have authority over the network, that is LAN or WAN. The size and format of these addresses vary depending upon the network. For example, Ethernet uses a 6 byte, which is equivalent to 48 bits physical address that is imprinted on the network interface card, that is NIC. Local Talk, that is Apple, however, has only a 1 byte dynamic address that changes each time the station comes up. MAC addresses are unique 48 bits hardware number of a computer, which is embedded into a network card, that is NIC, during the time of manufacturing. MAC address is also known as physical address of a network device. According to IEEE standard, data link layer is divided into two sublayers: logical link control sublayer, that is LLC, and media access control layer, that is MAC, out of which MAC address belongs to media access control sublayer. What is the format of a MAC address? As you can see at the bottom of the presentation, there is a 12-digit hexadecimal number, which is a 6 byte binary number, which is mostly represented by colon hexadecimal notation. First 6 digits, as you can see in the presentation, 3C, 5A, B4 of MAC address identifies the manufacturer, called as OUI, Organizational Unique Identifier. IEEE Registration Authority Committee assigns these MAC address to its registered vendors. For example, CC46D6 belongs to Cisco, 3C5A B4 belongs to Google, 3C D9 belongs to HP, etc. Now, the rightmost 6 digits, which are blank in this presentation, represents network interface controller, which is assigned by the manufacturer. As discussed earlier, MAC address is represented by colon hexadecimal notation. There are 3 types of MAC address: unicast, multicast, and broadcast. I will tell you in one sentence what these addresses mean. Unicast. A unicast addressed frame is only sent out to the interface leading to specific NIC. Multicast address allows the source to send a frame to a group of devices. Broadcast. Frames which are destined to MAC address FF, 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 6 times FF pair will reach every computer belonging to that LAN segment. So let us move on to next address, which is logical address. What are logical address? Logical addresses are necessary for universal communications that are independent of underlying physical networks. Physical addresses are not adequate in an internetwork environment where different networks can have different address formats. A universal addressing system is needed in which each host can be identified uniquely regardless of the underlying physical network. The logical addresses are designed for this purpose only. A logical address in the internet is currently a 32-bit address that can uniquely define a host connected to the internet. Make sure that this sentence which I am going to tell right now is very important. No two publicly addressed and visible hosts on the internet can have same IP address. Is it possible that you and your friend lives in the same house? In the same way, no two uniquely identifying devices can have same IP address. There are two types of IP address: IPv4, which means IP address version 4, and IP address version 6. IP address, that is IPv4, is further divided into 5 classes, class A to class E. We are going to discuss about these classes in the upcoming lectures. The next one is the port address. The IP address and the physical address are necessary for a quantity of data to travel from a source to the destination host. However, arrival at the destination host is not the final objective of data communications on the internet. A system that sends data from one computer to another computer is not complete. But how? Today, computers are devices that can run multiple processes at the same time. You might be using Gmail, simultaneously you might be using Microsoft Word, Office, or even playing a game. That is why the end objective of the internet communication is a process communicating with another process. For example, computer A can communicate with computer C by using Telnet. But at the same time, computer A communicates with computer B by using FTP. For these processes to receive data simultaneously, we need a method to label the different processes. In other words, they need addresses. In the TCP/IP architecture, the label assigned to a process is called a port address. A port address in TCP/IP protocol is 16 bits in length. Let us have a quick recap. We discussed what is a MAC address and its uses. We saw how logical address is used. We saw port address and its uses. To demonstrate a real-life example, let us consider someone from Amazon or Flipkart wants to deliver a packet to your house, right? The MAC address is the place of the region where you live. For example, suppose you are living in region A. The logical address is the address of your building or your house. So let us consider you live at house B in region A. But when the delivery person comes to your house, he wants that packet to get delivered to you specifically because that packet is ordered by you. Therefore, C is the address which is used to deliver that packet to you. And that is why all the three addresses are important in computer network. In the next lectures, we will see in detail what is an IP address, and we will see the working of IP address as well as different types of IP address. Let us start with IP address in computer networks. In this lecture, we will see what is an IP address, its notation, and types of IP address. So, you might have heard this term interchangeably when someone you talk with a technical person. He says, tell me your IP address. So, what is an IP address? An IP address works in an IP network just like a postal address works in the postal system. A postal address is the combination of two addresses, area address and house address. Area address is the group of address of all houses which belong to a particular area, and house address is the unique address of a specific house in that area. Each area is represented by a unique PIN code number in the postal system, right? PIN code helps in fast processing of a mail. In a central post office where thousands or in some cases millions of mails are received, forwarded and delivered daily, processing mail based on complete address is next to impossible. So consider a busy post office. The clerk doesn't read the complete address of the package to make his decision. He only pays attention to the PIN code. He reads the PIN code and drops the package in the container, which will be forwarded to the nearest post office of that area in the pin code. Same process is followed at the next post office, and so on and so on until the package reaches the post office which delivers packages in the destination area. At the last, the recipient's house address is used to deliver the package. So I hope you understand this example, and this exact mechanism is used in IP networks. So an IP address, or simply an IP, is a unique address that identifies a device on the internet or a local network. It allows a system to be recognized by other systems connected via the internet protocol. Just like the pin code, network address helps in fast processing of the packets. In the IP network, routers do exactly what post offices do in the postal system. Routers use a network address to find the destination network and host address to deliver the packets. So let us see an example of IP address. As you can see, many of the people who are using computers or mobile devices do not even know what is an IP address. If you tell them a number, they are just confused whether this is an IP address or not. So as I said in the previous lecture, there are two types of IP addresses. The first one is the IPv4 version, and the second one is the IPv6 version. IPv4 version was first used by ARPANET in 1983. It consists of 4 set of numbers from 0 to 225 separated by 3 dots. So when you visit let's say a random website www.google.com in your web browser, on Netflix, the system automatically translates the domain name netflix.com to the IP address 107.20.175.192 for that respective region. The range of IPv4 address is from 0.0.0.0 to 255.255.255.255. Now why it's 255? There are 8 bits and the maximum value of 8 bit is 256, 2 to the power 8. Therefore, 256 different values are available in single octet, which means 0 to 255. Obviously, IPv4 address is less secure than IPv6. As you can see in the picture, 172.16.254.1 is the IPv4 address. 172 is then represented in binary, 16 is then represented in binary, and so on. So that octet of 8 bits is 1 byte, and therefore since there are 4 different numbers 172, 16, 254 and 1, there are 32 bits, which is 8 into 4 bits. Therefore there are 32 bits IPv4 address. This notation of IPv4 address is known as dotted decimal notation. Now, what is an IPv6 address? The version 6 of IP address is the most recent version, which was initiated in 1994. It contains 8 sets of 4 hexadecimal digits and uses colons to separate each block. So in the image you can see there 2001 colon db8 colon 1234 colon 152c colon and so on. Therefore, number of possible IPv6 addresses are 3.4 into 10 to the power 38. That's a huge number, and obviously IPv6 address is more secure than IPv4 address. So let us have a quick recap. I hope you understood the example of IP address that I had just demonstrated using the pin code and the area. Then we saw what are IP address, types of IP addresses, v4 and v6. And finally, we saw in detail what does it mean by version 4 and version 6 and the differences between them. In the next lecture, we will talk in detail about different classes of IP address. Remember, in this lecture, we are going to study the different classes of IPv4 address. In the last lecture, you studied what is exactly an IP address and the two types of IP addresses, namely IP version 4 and IP version 6. So, let us begin with the 5 classes of IPv4 addresses. IP address is an address having information about how to reach a specific host, especially outside the LAN, that is a local area network. An IP address is a 32-bit unique address having an address space of 2 raised to 32 bits. So it is a long IP address. Generally, there are two notations in which an IP address is written, dotted decimals and hexadecimal. So you can see here, this is dotted decimal 126.255.255.254. Some points that need to be noted about dotted decimal notation are the value of any segment is between 0 to 255, since these are 4 octets and each octet has 8 bits, so the maximum value is 256. That means 0 to 255 value. There are no zeros preceding the value in any segment. For example, since the maximum value is 126, this is an example, since the maximum value is 126, and if you want to write 54.255.255.254, you cannot write 054. That is wrong. So let us begin with the classful addressing. The 32-bit IP address is divided into 5 subclasses. These are class A, class B, class C, class D and class E. You can see there are 4 octets. One octet is 8 bits, that is byte 1. Therefore, this is a 4-byte IP address or 32-bit IP address. Each of these classes has a valid range of IP addresses. Class D and Class E are reserved for multicast and experimental purposes. The order of bits in the first octet determine the class of IP address. Now, an IP address is broadly divided into two types, network ID and host ID. The class of IP address is used to determine the bits used for network ID and host ID and the number of total networks and each host possible in that particular class. So depending upon the network ID, the number of hosts and the number of networks are determined in a particular range. Note that IP addresses are globally managed by Internet Assigned Numbers Authority, that is IANA, and Regional Internet Registries, that is RIR. While finding the total number of host IP addresses, 2 IP addresses are not counted and are therefore decreased from the total count because the first IP address of any network is the network number, whereas the last IP address is reserved for broadcast IP. This is an important point. For example, in class A, if the maximum value is 256, that means there are 256 number of IP addresses available. 2 IP addresses need to be subtracted because those are reserved for special purposes. In the next lecture, we will see in depth what are class A, class B, class C, class D and class E IP addresses. Let us start classes of IP address. In this lecture, we will discuss the 5 types of IP address classes. We will also see in detail what do these classes mean and how to guess the class of an IP address just by looking the numbers. IP address is an address having information about how to reach a specific host, especially outside the LAN. An IP address is a 32-bit unique address having an address space of 2 raised to 32. Generally, there are two notations in which IP address is written, dotted decimal notation and hexadecimal notation. Some points that need to be noted about dotted decimal notation are that the value of any segment is between 0 to 255 as we have discussed in the previous lecture, and there are no zeros preceding the value in any segment. For example, if the number is 054, it should be written as 54. So why classes of IP address are important? The 32-bit IP address is divided into 5 subclasses as you can see on the screen. These are class A, class B, class C, class D and class E. Each of these classes has a valid range of IP address. Classes D and E are reserved for multicast and experimental purposes respectively. The order of the bits in the first octet determines the class of an IP address. IPv4 address is divided into two parts: network ID, that is net ID, and host ID. The class of IP address is used to determine the bits used for network ID and host ID. Each internet service provider or network administrator assigns IP address to each device that is connected to its internet. Note that IP addresses are globally managed by the Internet Assigned Numbers Authority (IANA) and Regional Internet Registries, that is RIR. While finding the total number of host IP addresses, two IP addresses are not counted and are therefore decreased from the total count because the first IP address of any network is the network number, whereas the last IP address is reserved for broadcast IP. Let me repeat this sentence once again for you. If you want, you may note down because this is very important. So here it goes. While finding the total number of host IP addresses, two IP addresses are not counted and are therefore decreased from the total count because the first IP address of any network is the network number, whereas the last IP address is reserved for broadcast IP. Now let us move on to the first class, which is class A. IP addresses belonging to class A are assigned to the networks that contain a large number of hosts. The network ID is 8 bits long, whereas the host ID is 24 bits long. The higher order bit of the first octet in class A is always set to 0. The remaining 7 bits in the first octet are therefore used to determine the network ID. Therefore, the total number of network IDs is 2 raised to 7, which is equivalent to 128. The 24 bits of host ID are used to determine the host in any network. The default subnet mask for class A is 255.x.x.x. Now you may have a question, what is a subnet mask? Don't worry, we are going to talk about subnetting and subnetting masks after this lecture. Note that 0.0.0.0 and 127.xyz are special addresses as we have discussed a couple of minutes before. The next is class B. IP addresses belonging to class B are assigned to the networks that range from medium-sized to large-sized networks. The network ID is 16 bits long and the host ID is 16 bits long. Higher order bits of the first octet in class B is always set to 10. Therefore, there are 14 bits remaining which are used to determine the network ID. The 16 bits of host ID are used to determine the host in any network. The default subnet mask for class A is 255.255.x.x. Since 14 bits are used to determine the network ID, total number of network ID is 2 raised to 14 and total number of host IDs is 2 raised to 16 minus 2. Now why minus 2? We have already discussed in the previous slide. The next one is class C. IP addresses belonging to class C are assigned to small sized networks. The network ID of class C is 24 bits long and the host ID is 8 bits long. Therefore, there are available hosts are 2 raised to 8 minus 2, which is 256 minus 2, that is 254 host IDs are available for class C. The higher order bits of the first octet of IP address of class C are always set to 110. The remaining 21 bits are used to determine network ID. The 8 bits of host ID is used to determine the host in any network. Therefore, the default subnet mask for class C is 255.255.255.x. The fourth class is class D. IP addresses belonging to class D are reserved for multicasting. The higher order bits of the first octet of IP address belonging to class D are always set to 1110. The remaining 28 bits are used to determine network ID. The 28 bits of host ID are used to determine the host in any network. Therefore, total number of network IDs is 2 raised to 28. Finally, moving to the last class, that is class E. IP addresses belonging to class E are reserved for experimental and research purposes. IP addresses of class E range from 240.0.0.0 to 255.255.255.254. This class doesn't have any subnet mask. So if anyone asks you which class doesn't have any subnet mask, the obvious answer is class E. The higher order bits of the first octet of class E are always set to 1111. So I hope you are clear with all the classes. If you are not clear, you can always rewatch the videos again. So here is a quick recap. It's a quick table for the classful IP addressing. So as you can see, for the class A, the start address is 0.0.0.0 to 127.255.255.255. In the same way, you have to remember this table, and therefore you can see class B starts from 128.0.0.0. Class C starts from 192.0. Class D starts from 224.0. So suppose someone gives you an example. Let's say I'll take a random address 128.52.56.123. So if anyone asks you to which class this address belongs, you may say the first bit is the first octet is 128. So for sure this IP address belongs to class B. In this way, just by looking at the numbers, you can guess the class of IP address. Let us start networking practicals. In this practical, we will be learning how to find out your own IP address using command prompt. So let us begin. What is an IP address? An IP address works in an IP network just like a postal address works in the postal system. So a postal address is a combination of two addresses, area address and house address. In previous lectures, we have discussed about IP addresses and we have also discussed about the classes of IP address. If you remember, there are 5 classes of IP address, class A to class E. So let us see your IP address belongs to which class. Let us start by typing command prompt in your search box. Type command prompt, that is CMD, and press enter. Now you can see the command prompt has opened on your screen. So how to find out the IP address? There is one command especially for Windows which says ipconfig, which stands for IP protocol address configuration, and press enter. There is a lot of information to process, but we are interested in finding out our IP address. So you can see there is a content called wireless LAN adapter Wi-Fi. In that, we have to find out our IP address. Do not get confused with the Wi-Fi here because the IP address of your PC is same for all other connections. So you can scroll down and you can see the IPv6 address. I have highlighted. So this is the version 6 address, which is the recent address. If you come down, you can see the IPv4 address, that is the 4th version address. And now the IP address of my computer or my PC can be different from your lab environment. So my computer's IP address is 192.168.43.182. Can you give us a moment and let us imagine that this IP address belongs to class B. But we have seen that the class B IP address doesn't start with 192. So this must be the IP address belonging to class C. IP addresses belonging to class C are assigned to small sized network. Yes, and my house is a small sized network. So the default subnet mask for class C is 255.255.255.0, as you can see on the screen, and the default gateway is also mentioned as 192.168.43.200. This was all about finding the IP address of your own PC. In the next practical, we will see how to find out the MAC address or the physical address of your machine. Welcome to Networking Practicals. In this practical, we are going to see how to find out the physical address of your machine, that is the MAC address. MAC address is a 12-digit hexadecimal number, that is a 6-byte binary number which is mostly represented by colon hexadecimal notation. So go to the search window and type command prompt and press enter. You can see it is C:/users/admin. Now what is admin? Admin is the name of my computer, the person who is using this PC and the person who is logged into this account right now. This name may change at your environment. So the command to find out the MAC address is similar to command finding out IP address with a slight difference. So type ipconfig/all. Before pressing enter, if you're using a Linux based machine or Ubuntu based machine, then the command to find out the IP address is ifconfig. It's not ipconfig. So now press enter. A lot of stuff appears on the screen, and do not worry, we will tell you how to calculate the MAC address. So in the first column you can see the host name. It is the name of my PC. It's not admin because it's a name by the manufacturer. Coming down to Ethernet adapter Ethernet, you can see media state is disconnected. Now what does that mean? That means that right now nothing is connected externally to my computer. Not a printer, neither USB, nothing. So if anything gets connected to my computer and external media, my MAC address would be 3464A9C089. Now you can see the MAC addresses for wireless LAN adapter local area connection *3 is different than the MAC address for Ethernet adapter. This happens because Windows creates virtual connections which are reserved for specific purposes, and only in such cases the MAC addresses can change because each connection has its own MAC address. Coming down, to wireless LAN adapter Wi-Fi. It's a big information table. There you can find the physical address. That is ECOEC449EC-E3. That is the MAC address of my PC currently in which I am logged in. You can see the dynamic host configuration protocol is also enabled for my PC, which clearly means that DHCP server can assign IP addresses dynamically. And yes, auto configuration is also enabled. In the last lecture or in the previous practical, we have used ipconfig command to find out the IPv6 address, and you can see the IPv6 address is same. Then we have find out the IPv4 address, and you can cross check that the address is same in this lecture as well as in the last lecture. And since my IP address belongs to class C, the default subnet mask is 255.255.255.0. The information also states some information about the DHCP server and the DHCP client. You can see that the DHCP server's address is 192.168.43.20. So you can see another one last column, Ethernet adapter Bluetooth network connection. Right now my device isn't connected to any other Bluetooth device, and hence it is showing disconnected. So if my device is connected to another physical device, then my physical address would be ECOEC449EC-C4. Now all these are hexadecimal digits. So we have seen two commands, ipconfig to find out the IP address and ipconfig all to find out the entire information in which your MAC address is also shown. In this lecture, we are going to see the IP protocol and different types of protocols. So let us begin with protocols. Now make sure that you become comfortable with protocols, because protocols are very important in computer networking in order to understand how computers communicate. So the first protocol that we are going to see is the Internet Protocol. The Internet Protocol, that is IP protocol or IP, is a set of rules for routing and addressing packets of data so that can they travel across networks and arrive at the correct destination. Data traversing the internet is divided into smaller pieces called packets. IP information is attached to each packet, and this information helps routers to send packets to the right place. Every device or domain that connects to the internet is assigned an IP address, and as packets are directed to the IP address attached to them, data arrives where it is needed. IP is connectionless and unreliable protocol, meaning it ensures no guarantee of successful transmission of data. We have discussed what are connectionless and connection-oriented protocols earlier. In order to make it reliable, it must be paired with a reliable protocol such as TCP at the transport layer. Now, TCP is a connection-oriented protocol, meaning it ensures the successful delivery of data. You cannot combine IP with UDP because both the protocols are connectionless protocols. The Internet Protocol is responsible for addressing host interfaces, encapsulating data into datagrams, and routing datagrams from a source host to a destination. For these purposes, the Internet Protocol defines the format of packets and provides an addressing system. You can see this is the image of an IP header. Each datagram has two components, a header and a payload. The IP header includes source IP address, you can see here, then destination IP address, and other metadata needed to route and deliver the datagram. The payload is the data that is transported. This method of nesting the data payload in the packet with the header is called as encapsulation. Now let us see what this IP header has got for us. You can see this is a 32-bit IP address, IP header. We have seen that IP address is 32-bit. So what is version? This 4 bits define the version of the protocol used, example IPv4 or IPv6. The internet header length, that is IHL, defines the length of the entire IP header. DSCP, that is differentiated services code point, this is the type of service the IP header is going to use. ECN is explicit congestion notification, which means it carries information about the congestion seen in the route. The total length describes the length of the entire IP packet, including the IP header and IP payload. IHL is used for IP header, whereas total length includes IHL value plus the length of the data. Now, identification. If IP packet is fragmented during the transmission, all the fragments contain same identification number to identify original IP packet they belong to. Now, what are flags? As required by the network resources, if IP packet is too large to handle, these flags tells if they can be fragmented or not. In this 3-bit flag, the MSB, that is the most significant bit, is always set to 0 because there are only 2 flags. 4 flags available, 0, 1, 2, 3 and 4. The fragment offset, which is this. This offset tells the exact position of the fragment in the original IP packet. Time to live, that is TTL. To avoid looping in the network, every packet is sent with some TTL value. Generally, the TTL value is 64. Now, this TTL value tells the network how many routers this packet can cross. At each hop, its value is decremented by 1, and when the value reaches 0, the packet is discarded. So, the packet can either be discarded before reaching the destination, and therefore it is not a connection-oriented protocol if IP is used alone. So, for example, the IP packet goes, the TTL value for IP packet is 64 from router A. Now, from router A, if the IP packet goes to router B, the TTL value gets decremented by 1 and becomes 63. This goes on until the IP packet tries to reaching the destination. Now, protocol. This protocol field tells the network layer at the destination host to which protocol this packet belongs to. That is the next level protocol. For example, protocol number of ICMP is 1, TCP is 6, that is transmission control protocol, and UDP is 17. Header checksum. This field is used to keep checksum value of entire data, which is then used to check if the packet is received or error free. The field is used to check some value of the entire header and not data. Then source address. 32-bit address of the center of the packet, and destination address is a 32-bit address of the receiver of the packet. Options. This is the optional field, it is not compulsory to field. Then the value of IHL is if the value of the IHL, that is header length, is greater than 5, then these options may contain values for options such as security, record route, timestamp, etc. So, let us start with the network layer protocols. The first protocol is Address Resolution Protocol. In this lecture, we will have an introduction to ARP. Before that, we would like to discuss what is address mapping, and then after that, we'll conclude this lecture with ARP's packet format. So, what is address mapping? In order to understand Address Resolution Protocol, you must know what is address mapping. The delivery of a packet to a host or a router requires 2 levels of addressing, logical and physical. We need to map logical address to its corresponding physical address and vice versa. This can be done by static mapping and dynamic mapping. Static mapping involves in the creation of a table that associates a logical address with a physical address. This address mapping table is stored in each device on the network. Static mapping has some limitations because physical addresses may change in the following ways. A machine could change its NIC card, which results into new MAC address. Or in some LANs, such as local talk, the MAC address changes every now and then. So to implement these changes, a static mapping table must be updated periodically, and this is a tedious task. And this is where dynamic mapping comes into picture. In dynamic mapping, each time a device knows one of the two addresses, that is IP address or MAC address, it can use a protocol to find the other one. And that protocol is nothing but ARP. It is a network layer protocol used to address resolution, or in simple words, map address mapping in TCP protocol. So now once we have discussed about address mapping, we will now see what is address resolution protocol. ARP is a network protocol used to find out the hardware address, which is nothing but the MAC address of a device from an IP address. It is used when a device wants to communicate with some other device on a local network. For example, on an Ethernet network that requires physical address to be known before sending packets. The sending device uses ARP to translate IP address to MAC address. The device then sends an ARP request message containing the IP address of the receiving device. All the devices on a local network segment can see the message, but only the device that has that IP address corresponds with the ARP reply, and it responds to that message. The sending device now has enough information to send the packet to the receiving end. In short, ARP translates the 32-bit physical address to 48-bit addresses and vice versa. So, as you can see, the position of ARP in the TCP/IP protocol suite is it lies along with the IP protocol and helps translating logical address to physical address. ARP resides in the network layer. So, now we will see the working of ARP. Make sure you observe the picture and listen to what I am telling. Step 1. When a source device wants to communicate with another device, source device checks its ARP table to find if it has already resolved a MAC address of the destination device. For example, in the picture, System A wants to communicate with System B, and therefore first it searches in its ARP table whether it has the MAC address of System B. Step 2. If ARP resolution is not there in local cache, the source machine will generate an address resolution protocol request. So, as you can see, System A has generated the message looking for physical address of a node with IP address 141.23.56.23. Step 3. The source broadcasts the address resolution protocol request message to the local network. So, as you can see in the picture, the request message is delivered to each and every PC on that network. Step 4. The message is received by each device on the LAN since it is a broadcast. Now each device compares a target protocol address with the source is trying to communicate with its own protocol address. So those who do not match will drop the packet without any action. Step 5. When the targeted device checks the target protocol address, it will find a match and will generate an address resolution protocol reply message. So as you can see in the first picture, System A has requested a broadcast message to each and every computer on the system. System B finds a match because System B's IP address is 141.23.56.23. So B says, hey, it's a match, and therefore B replies to A's broadcast message with its own MAC address. So in the step 7, the destination device sends the ARP reply message, and it will not be a broadcast message, but it will be a unicast message. This is very important. So source sends the broadcast message, whereas the destination always replies back in unicast message. Now step 8. The source machine will process the ARP reply from destination. So once System A receives the reply that System B's IP MAC address is A4:6C:F4 54:59:83:AB. Now what system A does? System A now gets that OK. So the machine with IP address 141.23.56.23 has a MAC address of A4:6E:F4:59:83:AB. So system A will store these two values in its ARP cache table. And the last step, the source machine will update its address resolution protocol cache with the sender hardware address and the sender protocol address it received via ARP reply message. So this is how ARP works. So let us have a look at ARP packet format. Hardware header or hardware type. This is to specify the kind or the type of hardware used by the local network for transmitting the ARP messages. The next is the protocol type. It is used to assign a fixed number in this field. IPv4 has a number 2408. Hardware size. This is the length in bytes for the MAC address. Generally, we see the Ethernet has a MAC address of 6 bytes long. Protocol size or protocol length. It represents the length of the IPv4 logical address. Then operation request. This is the logical address in bytes. It specifies the nature of the ARP message. Then sender hardware address or sender MAC address. Layer 2 address for the device sending the message. Then sender IP address. Protocol address in the IPv4 for the devices sending that message. And target hardware address is nothing but the layer 2 address of the receiver. And target protocol address, that is target IP address, is the protocol address for the intended receiver. In this lecture, we first saw what is address mapping, then we saw how ARP works and why do we need ARP, and we also saw the broadcast and the unicast messages, and finally concluded our lecture with ARP packet format. In the next lecture, we will talk about a different protocol, which is Dynamic Host Configuration Protocol, DHCP, which is used for assigning dynamic IP addresses in a computer network. Let us start with Dynamic Host Configuration Protocol, that is DHCP. So, in this lecture, we will learn to describe what is DHCP, components of DHCP, why we require DHCP, and advantages of DHCP. So, what is DHCP? As the name suggests, it is a protocol used for dynamically configuring the hosts on the network, such as workstations, personal computers, and printers. DHCP can help in assigning various types of information such as routing information, directory services information, and default web server and mail servers. However, the most important and commonly used information for which DHCP is used is the IP address and subnet mask information. In addition, DHCP can coexist with statically configured hosts with fixed IP addresses. DHCP can also carry out the allocation of certain configuration information to a host on a permanent basis. To accommodate both types of computers, DHCP makes use of a client-server approach. So make sure that if anyone asks you which approach is used by DHCP, it is client-server architecture. Thus, DHCP allows the use of computers that run several softwares as well as computers that run client software. Moving on to the components of DHCP. The use of DHCP on the network requires the following three components. As you can see on the screen, DHCP server, DHCP client, and DHCP relay agent. So what is a server? It assigns the IP address and other information to the clients when they request for information. DHCP client. It communicates with the DHCP server to get the desired information regarding its configuration. This communication can take place when the computer starts. The user of the DHCP client can also initiate a DHCP client request to the DHCP server to renew its information. And the final is DHCP relay agent. It is used to relay client requests to the DHCP server. When is client required or relay agent required? This is required when the DHCP server is yet to assign the client an IP address. Without an IP address, a client cannot use IP routing on its own. A DHCP relay agent helps the client to communicate with the DHCP server when the client does not have an IP address. Let us understand the DHCP process. First, I will tell you the explanation of the picture that you can see on the screen. The client sends a DHCP discover request to the server. Server replies back with DHCP offer. Then client sends DHCP request, and finally server replies back with DHCP acknowledgement. This is how it works. But I am sure that you won't be able to get the clear idea of DHCP process. So here's an example. Imagine a room full of footballers who came there to get their jersey numbers. Let us say there are 6 people in the room, 5 out of which are normal team players and one is the captain of the team who gives each player his number. When a new player comes in the room, he wants his jersey number because he is going to play football but doesn't know who the captain is. The new player will get his jersey number in the following 4 steps. Since the new player doesn't know who he should ask, he simply shouts at everyone, "Is there anyone who can give me a jersey number? Please reply." Everyone present there will listen to him, but only the captain will respond. The captain will shout back at him, "Are you okay with the number 10 for one match?" Since the captain shouted, everyone including the new player will listen to this. The new players will then confirm by shouting, "Yes, I am okay and ready to use 10 number for one match." The captain will then shout back for everyone to hear, "Alright, start using your jersey number 10. Thus, the new player got his jersey number in these 4 easy steps. In networking analogy, the team of 6 players in a room is a network and each player is a node, say a personal computer. The captain is a DHCP server and the jersey number is the IP address. When a new PC joins, it is in need of an IP address to be able to use the network. But it doesn't know which node is the DHCP server and therefore it relays a DHCP discover message asking, "Can someone here give me an IP address?" The message is sent to 255.255.255.255, which is the networking jargon for everyone. So everyone receives the message, but only the captain, that is the DHCP server, replies. Since the new node doesn't have an IP yet, the DHCP server has no choice but to reply to all with a DHCP offer message. So are you okay with using IP 192.168.1.10 for 4 hours? The message is received by all the personal computers including the new PC that requested the IP. Now the node has to reply if it is okay with using the IP given by the server. Therefore, it shouts back at everyone with a DHCP request message saying, "Okay, cool, I am okay with using the IP for 4 hours. Note that the node has only replied back, that is, it is okay with using this IP, but it hasn't yet started using it. The server now shouts back a DHCP acknowledgement message saying, "Alright, start using your IP." Since the new node doesn't have an IP yet, the DHCP server again replies to all. And finally, the new node starts using IP. The DHCP server allocates IP for a fixed duration of time which IP renewable or reallocation will take place. So in this way, this is the DHCP process that carries out in real life. What are the advantages of using DHCP? It sets free the network administrator from the duties of setting up the configuration information. Then it avoids this, and sometimes the same IP address is assigned to 2 different hosts. DHCP makes sure that no 2 hosts are assigned with the same IP address. DHCP is compatible with other devices such as mobile, iPad, laptop, computers, etc. And most importantly, DHCP allows IP addresses from a pool of IP addresses. So, the quick recap of this lecture would be, the real life example that I demonstrated a few minutes ago. Make sure you understand the DHCP process and the operation and the technical knowledge of DHCP. In the next lecture, we will see Internet Control Message Protocol, also known as the complaint box of networking. So let us start learning Internet Control Message Protocol, that is ICMP. In this lesson, we will see what is ICMP v4 protocol, that is the version 4. Then we will see ICMP encapsulation, ICMP message format, error reporting messages, and the most important, ICMP echo request and echo reply. What is ICMP? ICMP is a transport level protocol within the TCP/IP model which communicates information about network connectivity issues back to the source of the compromised transmission. It sends control messages such as destination network unreachable, source route failed, and source quench. It uses a data packet structure with an 8-byte header and variable size data section. ICMP does not attempt to make IP a reliable protocol. It simply attempts to report errors and provide feedback on specific conditions. ICMP messages are carried out as IP packets and are therefore unreliable. So let us start with ICMP v4 encapsulation. ICMP operates in the transport layer, but its messages are not passed directly to the data link layer. Instead, the messages are first encapsulated in IP diagrams and then sent to the lower layer. The ping command uses ICMP as a probe to test whether a station is reachable. Ping packages an ICMP echo request in the datagram and sends it to the selected destination. The user chooses the destination by specifying its IP address or name on the command line. When the destination receives the echo request message, it responds by sending an ICMP echo reply message. If a reply message is not returned with a set of time, ping resends the echo request several more times. If no replies arise at the end, ping indicates that the destination is unreachable. Another utility that uses ICMP is traceroute, which provides a list of all the routers along the path to the specified destination. Now, let us have a look at ICMP message format. As you can see on the screen, the header of an ICMP message is 8-byte long and the data section is of variable size. The general header format for each ICMP message is different, but the first 4 bytes are common to all the message types. First one is type. This 8-bit field is used for defining the types of messages. Second is code. This 8-bit field is used for specifying the reason for the particular message type. The last common field is the checksums field, which is 16-bit long. The information to find the original packet that had error included in the data section of the error messages, whereas the data section in the query messages contains extra information depending upon the type of the query. Now you may ask a question, what are error reporting messages? So if a utility is using ICMP and if the destination is unreachable, then it reports back with an ICMP reply message that the destination is unreachable. Then source quench, time exceeded, parameter problems, redirection are a few examples of error reporting messages. Basically, ICMP is like a control box which replies back with error messages. Let's conclude our lecture with ICMP query messages. ICMP can diagnose some of the network problems. This is in addition with the error reporting feature. Such a diagnosis is done through the query messages. Query messages is a group of different pairs of messages as you can see on the screen. Echo request and reply, timestamp request and reply, address mask request and reply, router solicitation and advertisement, information request and reply message. ICMP echo request and ICMP echo reply is very important. So what are these messages? This pair of query messages has been designed for the diagnostic purpose. This pair of messages is utilized by the network managers and users for identifying network problems. This pair of query messages would determine whether two given systems, either hosts or routers, can communicate with each other or not. The communication will take place, so listen carefully. A host or a router sends the echo request message to another host or router it wants to communicate to. The host or the router which receives the message replies back with ICMP echo reply message and sends it back to the original sender. We can also use the echo request echo reply pair to determine if the IP level communication is present or not. So you can see the client sends the ICMP request message to the server and server replies back with ICMP reply. ICMP together works with IGMP, IP, ARP in the network layer also. Let us have a quick recap to our lecture. We saw what is ICMP protocol. We saw that ICMP is the error reporting mechanism for the TCP/IP model. Then we saw the ICMP message format and the error reporting messages, and also saw the working of ICMP echo request and reply. In the next lecture, we will actually see how your data packets are sent from one router to another router using the routing protocol. Let us start with routing information protocol and open source shortest path first protocol. What is routing information protocol? It is a dynamic routing protocol which uses hop count as a routing metric to find the best path between the source and the destination network. It is a distance vector routing protocol which has AD value 120 and works on the application layer of the OSI model. You might have a question, what is a hop count? Hop count is the number of routers occurring in between the source and the destination network. The path with the lowest hop count is considered as the best route to reach a network and therefore placed in the routing table. For example, if you want to go from Chennai to Delhi, now there are two paths available. Let us consider first you go to Bangalore, then to Pune, then to Gujarat, and then to Delhi. The second path is you start from Chennai, go to Bangalore, go to Delhi. So these are the two paths. Which path you will choose? Obviously the shortest path or the path with minimum hop count. In the same way, RIP prevents routing loops by limiting the number of hops allowed in a path from source and destination. The maximum hop count allowed for RIP is 15 and hop count 16 is considered as network unreachable. What are the features of RIP? RIP updates of the network are exchanged periodically, then updates are always broadcasted, full routing tables are sent in updates, and routers always trust on routing information received from neighbor routers. This is also known as routing on rumors. So you might have guessed the disadvantage. Right, if one table entry is wrong, it will affect all the routers in that network. And that is why we prefer OSPF protocol, that is open source shortest path first protocol. Now let us see what is meant by OSPF. OSPF is another interior routing protocol. It is an intra-domain protocol and is based on the link state routing. For handling the routing efficiently and in a timely manner, the OSPF divides an autonomous system into different areas. What OSPF could do is the main question. OSPF provides solutions to most of the drawbacks of RIP. Using OSPF, we can scale up the routing architecture well beyond maximum 16 hops which were previously supported by RIP. Rather than exchanging node reachability, OSPF routers exchange link state information. Through the link state information, Each router maintains a own copy of the network topology. From this link state database, it is possible to find the shortest routing path. Now for those of you who are familiar with the OSI routing scheme, many of the features supported by OSPF are similar to the OSI's routing protocol. The original versions of OSPF are actually derived from some of the earlier versions of the ISIS protocol. What are the features of OSPF? Type of service routing, which is mean it is possible to configure different routers to support different type of service requirements. The next is load balancing. When multiple routes are available, traffic can be evenly distributed over the routes. This would obviously result in a higher network efficiency. The next is subdivision of autonomous systems. It is possible to further divide the system into logical areas. This would improve the management of large autonomous systems. The next is security. The data exchanges in OSPF are authenticated. So only those hosts intended for the routing network are included in OSPF routing path. The fifth one is the host. OSPF supports specific network and subnetwork routing. And the last is that OSPF is an open specification. In the figure, you can see that OSPF has a backbone area, area 0, and the other areas are divided areas of an autonomous system. So we saw why do we need routing protocols. We saw what is RIP. We discussed the advantages and disadvantages of RIP. To overcome the disadvantages of RIP, we introduced OSPF, and we also saw the features of OSPF. Let us continue with the networking practicals. In this practical, you will learn how to find out a trace route from your PC to the target domain. So without any wasting much time, let's dive into the command prompt. You might be wondering, what is traceroute? In computing, traceroute and tracert are computer network diagnostic commands for displaying the route and measuring transit delays of packets across an internet protocol network. So once you have launched the command prompt, type tracert, TRACERT. Make sure you have to just type the domain name, and here we are using flipkart.com. If you press www. You'll get an error because tracert works on the domain, and press enter. Now a router is working to find out the route between your PC and the target domain. So let us wait till the result arrives. So as you can see on the screen that our computer has successfully completed the trace route. Now let's interpret the results. You can see that the first request was sent to IP address 192.168.43.200. That router tried sending the request, but the second request timed out, and therefore it tried again after 93 milliseconds, and the next hop was at router 10.71.249.2. After that, the next hop was at 172.25.19.13. The next hop 172.26.46.184, and the second last hop is 172.17.120.4. And finally there were lots of request timeout errors, and finally it reached our destination 163.53.78.128, which you can see it is the IP address of Flipkart. So as you can see, there were total 6 hops between the destination: first, second, third, fourth, fifth, and the final one. So in this way, traceroute command has got executed.
Let's start with a new section, Sockets. In this section, you will learn about the basics of sockets. A socket is one endpoint of a two-way communication link between two programs running on the network. A socket is bound to a port number so that the TCP layer can identify the application that data is destined to be sent to. An endpoint is a combination of an IP address and a port number. In layman's language, think of it as a gate out of thousands of gates in an apartment. The primary purpose of socket is to connect one of the endpoint of a pipe to the end user, that is an application. To identify a socket, you have to mention two primary things, IP address and a port number. As you can see, in a simple one-to-one network, a system usually has a single IP address to which all the endpoints of a program connect. Port number comes in handy in identifying socket for specific application, service in an application. A unique combination of both is used to identify a socket. At any point of time, application can create or possess multiple sockets, which can perform different operations like sending or receiving data from others. A socket is a unique identifier of an application in a network. An application is just a program running on a device. That device is identified with its IP address unique in the network. The application is identified with a port number unique within that device. If you combine both, you will identify the application over the internet. On your screen, you can see the socket is written as IP address : port number, like 172.217.7.238:80, where 80 is the port number. In this diagram, you can see application 1 sends the data to IP number 192.168.16.21 of application 2 with port number 100, while application 2 sends the data to IP number 192.168.1.1 of application 1 with port number 80. In simple terms, think of your house as a system and you are the application in it. Now, you want to send a letter to your friend in another house. Let's suppose he is in some other state. What you would put on the envelope is his name and address. Now, his home address can be considered as the IP address via which we can identify the system that is home uniquely. But the application, that is person to which that information is sent, is identified by the socket, that is his name. The socket name uniquely defines the application, that is the person. Because sockets are the means by which computers on a network communicate, they open your computer to attack. The simplest possible attack is denial of service. Another common attack is to exploit a vulnerability in a particular program listening at a port. Sometimes it's possible to trick a listening server program into allowing unauthorized access to that program or even the whole computer. The hacker either wants data on the server or wants to use the machine as a mule, that is to launch further attacks from that machine. On your screen, you can see socket structure. I am not going into the deep of socket structure, but I will give you an overview of what is a socket structure. The socket structure consists of 5 fields. The first is family. Family field is used for defining the protocol such as IPv4 or IPv6 or other Unix domain protocols. Type. This field is used for defining the type of sockets such as stream socket, packet socket or raw socket. Next is the protocol. This field is usually set to 0 for TCP and UDP. Local socket address. It is used for defining the local socket address, that is the combination of local IP address and the port address of local application program. Remote socket address. It is used for defining the remote socket address, that is the combination of remote IP address and remote port address of a remote application program. Let us have a quick recap of what we learned in this lecture. We started with the definition of socket. Then we saw the importance of sockets in computer networking with a real-life example. At the end, we had an overview of socket header. What's next? Next is a completely new section, the application layer protocols. Let's start with the application layer protocols. In this lecture, we are going to learn the file transfer protocol. The file transfer protocol, that is the FTP, is a standard network protocol used for the transfer of computer files between a client and a server on a computer network. If requirement is to send a file from one to another machine, that is a computer, just follow a few set of instructions to do that. And that set of instructions is abide by FTP protocols, that is the rules to be followed. If you don't have these rules, you have to take care of many aspects of internet security and data inconsistency by yourself for your requirement. FTP is a protocol based on the TCP dedicated to transfer files. FTP can be used between different operating systems and in most cases requires authentication, that is username and password. Sometimes you can use anonymous FTP to download files. Using anonymous authentication, normally you can only download files. You cannot upload. In modern systems, it is considered insecure due to lack of encryption by default. Now, via internet, most of the times a better option in terms of security is SFTP. It is based on SSH connection. FTP uses the TCP port 21 for command transmission and the transfer of data using a dedicated connection. This connection to transfer data can be passive or active. Before the data connection can be established to send actual files, the control connection must be established. A specific process is followed to set up this connection and thereby create the permanent FTP session between devices that can be used for transferring of files. The control connection. The control connection uses very simple rules for communication. Through control connection, we can transfer a line of command or line of response at a time. The control connection is made between the control processes. The control connection remains connected during the entire interactive FTP session. Next, the data connection. The data connection uses very complex rules as data types may vary. The data connection is made between data transfer process. The data connection opens when a command comes for transferring the files and closes when the file is transferred. Let us have a quick recap of what we learned in this section. FTP is ideal for sending large files. It is reliable, fast, and doesn't have the size limits that can prevent large files from being sent via email. With the addition of security features and modern web-based file management, FTP is still a widely used method for transferring data. In the next lecture, we will move forward to HTTP and HTTPS. Let us begin with the application layer protocols. In this lecture, we will see the hypertext transfer protocol, that is the HTTP. The hypertext transfer protocol, HTTP, is a protocol used mainly to access data on the World Wide Web. It is a protocol for transferring your web pages which are designed using a language called HTML, which stands for Hypertext Markup Language. HTTP uses the services of TCP on the well-known port 80. HTTP version 1.1 is the most common used version today. HTTP works by using a user agent to connect to a server. The user agent could be a web browser or a spider. The server must be located using a URL. The URL always contains http:// at the start. HTTP is a client-server protocol by which two machines communicate using a reliable, connection-oriented transport service such as the TCP. HTTP can be implemented on top of any other protocol on the internet. The lifetime of a connection corresponds to a single request-response sequence. The pure HTTP server implementation treats every request as if it was a brand new request. HTTP pages are stored on your computer and internet caches. The pages load faster, but they are stored on systems that you don't have potentially control, like ISPs caching proxies. HTTP server is implemented by Apache HTTP server, Microsoft IIS, Jigsaw, Zope, and many others. HTTP functions as a combination of FTP and SMTP. Although HTTP uses the services of TCP, HTTP itself is a stateless protocol. The client initializes the transaction by sending a request message. The server replies back by sending a response. HTTP is called a stateless protocol because each command is executed independently without any knowledge of other commands. This is the main reason that it is difficult to implement websites that react intelligently to the user input. Now, we will discuss the advantages and drawbacks of HTTP. Starting with the advantages. HTTP is platform independent, which allows straight cross-platform porting. No runtime support required to run properly. It can be used over firewalls. For example, global applications. It's not connection oriented. There is no need for network overhead to create and maintain session state and information. Continuing with the drawbacks. Integrity is not there, so someone can easily alter with the content. HTTP is insecure as there's no encryption methods for it. Therefore, it's subjected towards the man in the middle and eavesdropping of the sensitive information. There's no authentication, so you will not have any clear idea with whom you are initiating a communication. Authentication is sent in the clear. Anyone who intercepts the request and can know the username and passwords being used. Now, let's have a quick recap of what we learned in this lecture. We started with the general definition of HTTP. Then we saw advantages and drawbacks of HTTP. What we observed was HTTP has more drawbacks than advantages. Therefore, in the next lecture, we will see the more encrypted version of HTTP, that is the HTTPS. Let us continue with the application layer protocols. In this lecture, we are going to see HTTPS, that is Hypertext Transfer Protocol, secure. A more secure version of HTTP is HTTPS. But before learning HTTPS, we should learn what is SSL. SSL secures connections between two computers. Each time a pair of computers want to connect securely, they will agree on an encryption key. This key is created randomly for each connection. In simple terms, SSL, which is Secure Sockets Layer, is one of the security technology which is used to establish a secure connection between web server and web browser. This secured link is in encrypted format, so it assures users that data which is passed between this link means web server and browser is private and original. SSL is an industry standard protocol which is used by several websites for protecting their online transactions with their customers. Essentially, an SSL certificate is a sign of trust displayed between your website. If your website has an online store and requires card payments, an SSL certificate is like a digital handshake between your site and theirs. This sign of trust allows your site to process their card payments securely. Google now requires all e-commerce websites to install an SSL certificate to ensure maximum safety. Google is even blacklisting certain sites that do not carry SSL certificates and lowers their Google ranking. SSL certificates, thankfully, can be found for free from Let's Encrypt. Let's Encrypt is a Google-sponsored initiative to provide SSL certificates freely. Coming back to HTTPS. HTTPS encrypts all the information that is sent and received. This can stop malicious users such as hackers from stealing the information and is often used on payment websites. HTTPS refers to the combination of HTTP and SSL to implement secure communication between a web browser and a web server. The HTTPS capability is built into all modern web browsers. The principal difference seen by user of a web browser is that in the URL, the address begins with https:// unlike http://. If HTTPS is specified, port 443 is used, which invokes SSL. When HTTPS is used, the following elements of communication are encrypted. First, the URL of requested document. Then, contents of document, contents of browser forms, cookies sent from browser to server and from server to browser. And last, the contents of HTTP header. Consider a scenario. In first case, you send a message to a friend via a mutual friend. Your friend receives the message and may respond back if needed. This is HTTP. Here someone can recover the message in the way from that mutual friend by some means like blackmailing or even gun pointing. Consider second case. You send the same message to a friend through the same mutual friend, but this time your mutual friend is being accompanied by the bodyguards and gunmen. That is the SSL encryption, which will only allow your friend to receive the message. Your friend receives the message and may respond. This is HTTPS. Here it is next to impossible to recover the message in any way, or simply eavesdropping is not possible due to bodyguards. Simply, HTTPS means that the requests made to the website are encrypted and cannot be decrypted unless the proper key is used, so as to prevent attacks like eavesdropping and man in the middle. Let's move on to advantages of HTTPS. In most cases, sites running over HTTPS will have a redirect in place. Therefore, even if you type in http://, it will redirect to an HTTPS over a secured connection. More secure than HTTP, obviously, because encryption is accompanied by HTTPS. SSL technology protects any user and builds trust, like I said in the real life example, like bodyguards. Each SSL certificate contains unique, authenticated information about the certificate owner. Now, let us have a quick recap of what we learned in this lecture. We started with SSL, then we moved forward to HTTPS. Then we took a real life scenario and explained the difference between HTTP and HTTPS, and thereby concluded with advantages of HTTPS.
Let us start learning domain name system. To identify hosts, IP addresses are cumbersome for humans to use and to remember. The internet supports the use of host names to identify hosts, both clients and servers. In order to be used by protocols such as TCP and IP, host names are converted into IP addresses using a process known as name resolution. There are different forms of name resolution in the internet, but the most prevalent and the most important one uses a distributed database system known as the domain name system. Basically, domain name system converts human readable domains like www.google.com into IP addresses. So let us have a quick example. I would like to ask you one question. Is it easy to remember your friend's phone number or his name? Right? It's easier to remember a name rather than a whole phone number. DNS is a distributed client-server networked database used by TCP/IP applications to map between hosts and IP addresses, and also vice versa. The DNS provides the control that allows clients and servers to communicate with each other, and also a protocol for allowing servers to exchange information. As you can see, this is the main root server. Let us consider a website admin.stanford.edu. Okay, so .edu is the domain name of that particular website. In .edu, there can be any number of college domains, for example, Stanford, Harvard, MIT, and many more. That is the root level. .edu is a root level, root authority. Then comes stanford.edu. Now Stanford stands for the domain name authority. Stanford is a specific domain. And finally, the admin, that is admin.stanford.edu, is a subdomain. So it is easier to remember admin.stanford.edu than to remember an entire IP address. Let us have a quick recap. From an application's point of view, access to the DNS is through an application library called Resolver. And DNS makes it easier to remember the website's name rather than the IP address.
Well done! You have successfully completed the first section of this course. I know the first section was quite tiresome and hard to understand for any novice learner. But don't worry, go through the videos and practicals once again and make your concepts all clear. Basics of computer networking are way too much very important for understanding the foundations of cybersecurity. As of now, congratulations on completing the first section. See you in the next section. Till then,